This will be a calculus review of the concepts of area and volume. We will be doing 4 to go through this review, and all of them will be based on region R, which you see defined as the bounded area with a curve, y equal e to the x minus 1, the line y equal x plus 2, and the y-axis. In the first problem, we'll be of R. In the second one, we will find the volume when R is rotated around the y-axis. In the third one, we'll find the volume when R is rotated around the line y equals -1. And finally, we'll find the volume of a solid which has R as its base. Cross-sections of this solid perpendicular to the x-axis are rectangles whose heights are half the length of their base in R. So we'll be doing 1 area problem and 3 volume problems. Let's get started. In the first problem, we are finding the area of R. And you see that I've drawn some Riemann rectangles. You'll remember this theory where we have widths in this case, which are dx, and lengths of the rectangles, which are the difference in the y value from the line down to the curve. And we'll be summing, as you remember, length times width plus length times width. So we start with the integral from 0 to 1.5052. And on your calculators, you'll want to do the intersection there of the curve and the line in order to get that x value. And again, we'll be taking the upper value, which is the line, the y value up to the line, minus the y value to the curve. So that formulation would be x plus 2 minus e to the x minus 1 quantity dx. And when we clean that up, we get integral from 0 to 1.5052 of x minus e to the x plus 3 dx. And when you put that in your calculators using Math 9, that should give you the value 2.143. And of course, this is area, so we're talking about units squared. Okay, let's go on to the problems. In problem 2, we are going to rotate our region R here around the y-axis, creating an interesting solid which has a cross-section which is circles on the lower part, and you see rings here above 2. So we're going to use our formulas for both disks and washers. So in the first part, we'll be integrating from 0 to 2 of pi times cap r squared y, where cap r is our radius over to the curve. And in the second part, we'll be going from 2 to 3.5052 of pi times that same cap r squared minus little r squared dy, where cap r is the x value over to the curve and little r is the x value to the line. Well, we are going to have to solve for that x value because all we have here is the y value. So let's isolate x. We have y equals e to the x minus 1. So when we add that 1 to the other side, we have e to the x, but we need to take an ln of y plus 1, and of course the ln of e to the x is just going to be x. So we have x is the ln of y plus 1. All right, that's the quantity which is going to be our big R. So let's go. We've got integral from 0 to 2 of pi times ln, we've got to square it in our formula, times y plus 1, ln squared of y plus 1 dy, and then our washer formula will be the integral from 2 to 3.5052 of that same, don't forget the pi, ln squared of y plus 1, and our x value over to the line is much easier to compute. It's simply y minus 2, minus y minus 2, quantity squared dy. And when we put that in our calculators, we should get 3.2332. Notice I'm using 4 decimals here so I don't incur round-off error. As you know, the AP exam wants 3 decimals of accuracy. 7.912. This is a volume, so of course this is units cubed. Okay, let's go on to the third one, where we are going to take this region R and we're going to rotate it this time around the line y equals -1, creating a very large solid which clearly has a cross-section which is a ring, so we're going to use our washer formula. And in our washer formula, again, these are going to be dx discs. I don't know if you can see that. There we go. I'll move it up a little bit. Dx discs, because we're rotating around a line which is parallel to the x-axis. So we have integral from 0 to 1.5052 of pi times cap r squared minus little r squared dx, where the big radius, now this gets a little bit complicated, but you're measuring the distance from this line y equal -1 all the way up to the line y equal x plus 2. So we're going to have to take the y value up to the line and add this 1, or you can think of it as the y value to the line minus a -1. So it's y to the line minus a -1. And then the y value for the little radius, we're going to be taking the y value to the curve minus a -1. Again, always thinking of upper minus lower. Y to the curve minus a -1. So when we put that in our formula, we have pi integral from 0 to 1.5052 of x plus 2 quantity minus the -1 has the effect of adding 1 squared minus e to the x minus 1, again adding 1, extending that radius. And cleaning that up, we have pi times the integral from 0 to 1.5052 of the quantity x plus 3 to be squared minus e to the x quantity squared dy, and I'm sorry, that's a dx in both cases. Let's make sure we have that dx. A little clarification there. Of course, the x's and the dx's have to match. When you put this in your calculator, you'll have e to the 2x would be easier to put in, and you will get 37.173. And of course, again, those are units cubed. All right, and on to our final example, which is an interesting solid where we are using the big region R as the base of the solid, and we have rectangles coming out of the page, and we know that the height or width, if you will, of those rectangles is half the length in R, where the lengths are perpendicular to the x-axis. So we remember our theory of volumes being really sums over cross-sectional areas, and all the other problems, the cross-sectional areas were circles or rings, which are circles minus circles. In this case, we have rectangles whose cross-sectional areas are given by length times width. So let's think about what these rectangles look like. These rectangles have lengths, which are the y value up to the line minus the y value to the curve. So that would be x plus 2 minus e to the x minus 1, or cleaning that up, x minus e to the x plus 3. All right, so let's put that in. We have integral from 0 to 1.5052 of the length, which is minus e to the x, plus 3, times the width, which we were told is half that length, so we have 1/2 of x minus e to the x plus 3, quantity dx, and let's write that as 1/2 integral from 0 to 1.5052 of the x minus e to the x plus 3, quantity squared dx, and when we put that in our calculator, we come up with 1.773 cubic units, a surprisingly small volume.